All right. Hello, everyone. I'm Andrew Jones, the CEO of Activated Research Company, and I'm joined here today with Daniel Lundberg,
Yeah.
a PhD candidate from MIT. So Daniel, hi. Thanks for coming.
Yeah, thanks for having me.
Well, it's great to have you here. It sounds like you've been doing some exciting work with carbon dioxide photoreduction and making renewable fuels and chemicals, something near and dear to my heart. So I'm excited to talk to you about this work and kind of what got you into this and where you see this going next. So once again, thanks again for coming on the show, and
Yeah, of course.
to our listeners, please keep subscribing and listening to what we're doing here. So Daniel, the work that we're going to be talking about today is primarily this paper that you worked on under the direction of Michael Strano, which is titled "The Universal Kinetic Mechanism Describing Carbon Dioxide Photoreductive Yield and Selectivity for Semiconducting Nanoparticle Photocatalysts." A lot of big words in there. Can you just first maybe describe for the readers or listeners here, maybe in a high level, what you were trying to do and what were the problems that you were looking at with this?
Yeah. So I guess what I'll start with my lab at MIT actually is really actually a pioneer and kind of the founder of the field of what's called plant nanobionics. So really the interface of living systems with nanotechnology, synthetic systems to try to augment kind of the capabilities of both. And so we have a lot of natural systems, a lot of plants in our lab, and that was kind of the inspiration for, okay, we want to make materials that are like plants that have all of these amazing properties, right? They can grow, they can strengthen, they can reinforce. They at least sequestering and incorporating atmospheric CO2, which is obviously very important that they do that. And so that was kind of the main background of the whole project is, can we make synthetic materials that have these same properties that are able to take, say, CO2 from the atmosphere, convert it under relatively ambient conditions with low partial pressures, and produce kind of monomeric units that can polymerize and grow into kind of strengthening and reinforcing material systems. And so we looked at it and said, has anyone really done anything like this? And of course, there's been kind of synthetic photosynthetic schemes that have been proposed, but nothing really to make materials that grow. And so when we looked at the literature specifically for photocatalysis, actually, we kind of saw this huge divide where a lot of people were performing these reactions and studying these really common photocatalysts that are, I would say, relatively active under kind of very extreme conditions, right? So super high partial pressures of CO2, higher temperatures, kind of extreme pH, so very low pH, very acidic, or on the flip side, very basic with a lot of coal scavengers, sometimes organic solvents, which was kind of very incongruous to the vision that we had of kind of ambient conditions, kind of just use what's there, so just water, sunlight, low concentrations of CO2. And so we were kind of stuck, actually. We didn't know kind of how to produce the molecules that we wanted. We were aiming for formaldehyde specifically as a reactive intermediate to then polymerize. And so after kind of a survey of the literature for what people had done at these kind of diverse and really, I would say, forcing conditions, we found that, okay, people have been able to make this small molecule that we want to make, but actually a lot of people don't test for it. And maybe of the 300 reports that we summarized, 15% of them mentioned formaldehyde as a product, but only 7% of them mentioned even attempting to test for formaldehyde. And that, of course, is related to a variety of different issues. One, kind of industrially, it's not so relevant, so people don't want it as a high value fuel like methanol, for example. And two, actually, are the analytical difficulties with detecting this molecule, which kind of brings us here, right, is kind of when people run these reactions, they sample gas with a GC, they sample liquid also with a GC, but if you don't have the right analytical techniques, right, you just will not see any kind of formaldehyde. And so kind of we knew that was one issue, and so we kind of said, okay, we think it's here. People have reported that it's here, but what tools do we need to detect it actually, the one molecule we want, and how should we go about doing this? And of course, that kind of gets us into the story of using the polyarc and using these kind of advanced quantitative techniques to really enhance our research, really actually enable the research that we were doing at MIT at the time.
Well, fantastic. So kind of at a high level, you're trying to mimic photosynthesis, right? So you have, and pretend like, I don't know much about this on the biology.
Yeah.
You have a leaf that kind of sucks in CO2 and it uses the sunlight to then create sugars, right? And so that's kind of the photosynthetic process. So you're trying to do that synthetically with these these nanoparticle catalysts. Is that right? And
Yeah,
get
yeah,
the
that's
sun
right.
and
Yeah,
okay,
exactly. So kind of just like plants, right? The leaf or like pine needles or whatever, where there's chlorophyll, right, is kind of a very complex chemical reactor. We want to take the reagents that we have, available to us in the atmosphere, right? CO2, water, sunlight, and make something. We were humble in the fact that we were not going to try to make glucose. Obviously, natural systems are so complex. The joke I always make is that nature's had millions, tens of millions of years to develop and fine tune these systems, and I have to write a thesis in 5, right? So
yeah,
yeah, our goal was to do kind of a simpler process, CO2 to just single carbon containing products.
okay. And it looks like you were successful. So you are able to take, I presume you bubble CO2 into a
Mhm.
water solution with these catalysts, and you're able to make chemicals and fuels or building blocks, formaldehyde,
Yep.
from that. Okay.
Yeah. Yeah.
Well, that's fantastic. So how did you, I know we talked a little bit before the
Mhm.
show, and you're a Minnesota guy just like me. So how did you get into this field, and what kind of motivated you to start working on this?
Yeah, so for me, it actually comes down to, and you brought up Minnesota, right? I'm from Minnesota. We grew up in the Twin Cities, but actually my parents are from kind of the north, I'll say northern Minnesota, northern Wisconsin. And so growing up, we always had this, like the best part of our summers, the best part of our weekends was going to nature, right? Going to state parks, going to Lake Superior, doing stuff outside, camping, fishing, skiing, of course. And so that kind of was one of the reasons that I wanted to pursue chemical engineering as an undergrad, because society has a lot of problems, and a lot of them are related to, say, like the industrial production or use of chemicals or fuels. And so with that, kind of I going to graduate school, I kind of looked for a research lab for me that was very familiar. I wanted to work in nanotechnology, but also had kind of been doing some work really on the cutting edge of what is possible in the chemical space. And so that drew me to the lab of Michael Strano to work on these materials.
Awesome, awesome. And there's a ton of talk right now, especially about taking CO2 and making materials out of it, or sequestering it. What do you think are the biggest challenges to specifically taking CO2 and making products and fuels out of it?
Yeah, it's definitely all about the money, of course, right? It's super
Yeah.
expensive when you're working with a dilute feedstock, right? It's kind of very, very difficult and very energy intensive to accumulate this product, concentrate it, and then kind of produce something from it. Of course, CO2 is kind of sits in this thermodynamic well where you need to, always be adding energy to it to make literally anything that you want. So that was kind of one thing. And so our perspective actually was, okay, we're not going to think about the industrial conversion, the industrial kind of collection of CO2 from the atmosphere, but actually focus on if we can, say, like use it to make materials or add value to kind of things that already exist, right? And so
Mm.
when you paint a building or you coat a pipeline, for example, we all know that synthetic materials do have a limited lifetime, right? They will degrade, they always do degrade. And actually, the reason that, say, you have to repaint a wall or recoat a pipeline or really any kind of infrastructure is not because the whole material fails, but it's because really a small kind of micro crack forms and then propagates to then expose, say, the underlying
Mm.
infrastructure to the elements in water, right? And so actually we're kind of synthesizing, coating, scraping off, recoating again, kind of
Mm.
all these like different surfaces, just because kind of a small fraction of mass actually degrades. And so we thought, hey, actually, if we could really introduce kind of a small growth rate or a small rate of CO2 incorporation and strengthening into these synthetic materials, we probably wouldn't need a lot of mass, a lot of conversion to actually really vastly extend the lifetime of these materials and also save on, say, the energy of making them in the first place and also the cost.
Hmm. And so tell me a little bit more about these materials, these nanoparticle catalysts.
Yeah. So there's a lot of different ways you can take the sun's energy to convert it into things, right? So PVs or photovoltaics will take sunlight to make electricity directly. We kind of operate under the same principle where we have a semiconductor or a nano lab. So of course we have to use the nanoparticles, which are kind of very high efficiency for this process. They absorb sunlight. They'll make an exciton, right? So they'll have an excited electron leaving a hole behind, and those two individual kind of particles or quasi-particles will then kind of migrate to the surface of these small catalysts and then be able to, the electron can reduce CO2 while the whole can perform kind of the other oxidative half reaction with water if water is there to do water oxidation. So that's kind of the
Okay,
scheme that we use to do CO2 conversion.
I see. And so you had, I'm looking at your paper here. You've got,
Mhm.
in some cases, things like titania with
Mhm.
gold on top of it, or
Yeah.
and is that the gold nanoparticles then that are absorbing the light and creating these holes?
So in our work actually, so the metal modifications were, it was non-photonic, so actually it was just the semiconductor itself, the kind of
Hmm.
bulk semiconductor that was absorbing the light.
Yep. Okay. Awesome. Tell me, you talked a little bit earlier about the analytical challenges and, formaldehyde. I've known that for a while, that,
Yeah.
it's typically done by liquid chromatography with some difficult derivatization reactions. What, do you think that is what held back some of this research? And I guess, what are the big analytical challenges that you saw when you were trying to do this?
Yeah, so I think absolutely that kind of holds back the research. So yeah, analytical difficulty with detecting formaldehyde, right? Everyone, everyone and their mother who's doing CO2 conversion uses gas chromatography to sample, say, the gas as well as the liquid in most cases, and they don't really try to look for anything else, right? So kind of on like, say, I would say, like, if you're an undergrad doing the reaction, the easiest thing to do is just sample the gas. Kind of a common metric is like the ratio of carbon monoxide produced to the ratio of methane produced, and that gives you kind of a broad understanding of how reductive and how active your material is. But kind of going beyond that, right? We don't care about CO, we don't care about CH4. We wanted these liquid products, these kind of higher value materials, and with that, right, if you have this GC and you know that it can quantify these carbon containing materials, you put the liquid in, and if you don't have kind of the polyarc, right, you will not see formaldehyde at all. You might see formate, you might see methanol, but you will not see formaldehyde. And I think for literature, right, they didn't really care about that. Methanol is certainly like a much higher value fuel, and so people just will see what kind of catalyst function and then say, okay, great, did it or did it not make methanol? And so
Yeah.
there really wasn't actually a need to analyze formaldehyde until, at least from our perspective, right, we wanted to actually turn CO2 into, or these little nanoparticles into kind of mimicking plant-like systems, biological systems that can kind of grow and strengthen. And so yeah, certainly it comes all the way back to people didn't care about it and people couldn't see it.
Yeah.
And so it's really easy to ignore the things that you just don't see.
Yeah, and maybe some low hanging fruit for you to pick off. I love that. Yeah.
Yeah.
So what questions still remain in this research, and where do you think it's going to go next?
Yeah, so kind of the questions for us are kind of the summary of the manuscript was that, yes, actually with these systems, we're able to detect formaldehyde as the product that we want, but we see this kind of really, I would say, frustrating trend where formaldehyde is the preferred product under the conditions that we operate under. But as you get higher and higher conversion and higher like, activity for CO2 reduction, you kind of shift the selectivity vastly and very far away from formaldehyde to have it be, really only a minor product. I think the most active material we saw had formaldehyde selectivity under 1%. So that's a huge shift. We actually reported the highest formaldehyde selectivity kind of ever for CO2 photoreduction at roughly 80%, if I have the numbers right, but of course they're in the paper. And so that was so we're kind of operating under this huge range where we're making the product that we want and we're making it selectively, but we would like to do it faster and accumulate more of it. And kind of the thing that we identified in the work was that kind of these nanoparticles are really, really oxidative as well, right? And so I mentioned that you have this electron to do CO2 reduction, but you also have this hole that can oxidize kind of water preferentially. But if you have carbon products in the system like formaldehyde, that hole can also kind of parasitically oxidize the species back to carbon monoxide or carbon dioxide as well. And so you end up kind of very figuratively spinning our wheels and putting energy in, but kind of just cycling through the product that we want. And so that's kind of the one thing that we're looking for now is actually kind of chemical schemes to be able to isolate and accumulate this reactive intermediate.
So, how far away are we from commercialization of something like this and being able to make our clothes with CO2?
Yeah, I like cannot give. I mean, we make our clothes with CO2, right? This shirt is 100% cotton, and so certainly there are great ways to use plants currently, but for us, kind of it is like the one major challenge is being able to kind of just accumulate this product in a rate that's fast enough actually. And so we did some kind of accompanying mathematical modeling and actually found that if we can just increase the catalytic activity or the amount of formaldehyde that we generate by 10 times, only one order of magnitude, we would actually be able to produce systems or coatings that on a mass per mass basis kind of incorporate and grow just as fast as plants do, right? And so that's slow to the naked eye, right? But that is certainly fast enough for plants to have, decades or even centuries of life. And so really for us, it was yeah, accumulating the formaldehyde at a rate that is faster. So that's kind of what we're working on at this point.
Yeah. Well, I love how this was kind of bio-inspired, and now you're using biology as a benchmark to measure your success here. That's great. You're right. And biology, of course, has had hundreds of millions of years to evolve. So you've done a lot.
Exactly. Yeah.
So maybe kind of switching gears a little bit more to you, and you know, I know for me it was a difficult decision whether to get a PhD or not. What would you tell other students or in college or high school who are looking to get into this field, and maybe pros and cons of that?
Yeah, I think if you can, make it through school, right, and you can support yourself and you can actually survive, it's kind of a huge pro, right? I learned how to be kind of a very amazing scientist at MIT, and that's something that I can say in retrospect, looking at all the, the mistakes I've made and the difficulties that I've had, 2, 3, or 4 years ago even. And so, like, really, yeah, I could not stress enough, like, continuing education into this field. Certainly the challenges that we face as society, are something that we need, what I mean, a lot of work on, a lot of kind of the best and brightest minds too. And I'll say for me personally, I don't think I could have made as large of an impact just with an undergraduate degree and just with, say, less education.
Well, we thank you for doing it and making this progress. So what do you want to see happen next? Just in general, I guess, with you're in your last year here and you're moving on. What do you say to the next group of students coming in and taking this over?
Yeah, so actually, I would like to encourage them, really greatly. There's a lot of traction, I think, on the science side, but also, maybe even more importantly on the policy side with some past legislation, in this year. And so there's a lot of money, there's a lot of time and a lot of effort, and a lot of smart people are really thinking about, say, the same problems. So I think it's a really, ripe space, a really encouraging space to work into, where, I believe that, one, it's a super pressing problem, but two, I do believe that we can, solve it.
Yeah. Well, I love your approach using sunlight directly, because I've looked at this as well. I did methanol to gasoline, methanol to olefins, and you can make methanol from CO2, but you pump a lot of energy into that. You pump in, 5,000 kilowatt hours per ton of CO2. In your opinion, do you think these direct, sunlight mechanisms are going to dominate over kind of the traditional approaches of just Fischer-Tropsch or methanol to gasoline that require a lot of, hydrogen, which is going to come from a lot of electricity? Have you thought about that? I know this is kind of an open-ended question, but
yeah. So we looked at the at least for the potential energy required for CO2 reduction in general, right? It's not so steep actually, and so direct kind of photocatalytic systems that are taking the sun's energy certainly can be more efficient than, say, just using a silicon photovoltaic, converting the sunlight to electricity, then using that electricity to power, say, some electrochemically driven process for CO2 reduction. And so there definitely is potential to kind of exceed that. But I mean, right now, right, like the most carbon that like the Earth is converting and cycling through is from living systems that are taking the sun's light. And so it definitely, is possible. It definitely is a promising space for, a lot of carbon to be absorbed, a lot of carbon to be sequestered.
Good point. I think that's a great place to leave this. Was there anything else that I missed that you wish I would have asked?
No, let me think. No, actually, I think that's it. I mean, I can talk more actually. So we're doing CO2 reduction, but we're also doing kind of methane oxidation, methane abatement as well. And so kind of doing essentially trying to make the same system where we take, instead of CO2 as a carbon source, methane, and then convert that, oxidize instead of reduce to formaldehyde, and kind of grow the same systems. And so we are kind of continuing to use the polyarc for that. We kind of still have the same desire to detect and analyze formaldehyde concentration, but kind of coming at it from a really, like, instead of an uphill perspective for CO2 reduction, kind of a thermodynamically downhill perspective, right? It's really easy to oxidize methane and actually over oxidize it past formaldehyde as well.
Yeah, it definitely wants to go all the way to CO2, doesn't it?
Yeah, all the way, yeah.
So you stop it at formaldehyde. So this would be used in kind of stranded methane sources where there's nowhere that, like I'm thinking of landfills or other places
exactly.
where methane is produced. Yeah,
definitely. So there's methane emission is very, it's a huge problem, right? So methane emission now accounts for, I'll say maybe like between like 20 to 30% of the warming that's happening like this year is from methane actually, and so it's kind of a small
Yeah.
gas by volume and by concentration in the atmosphere, but it's just so potent that actually
Yep.
kind of any emission really drives a lot of warming on a really short time frame. And so we want to take the same idea, sequester and convert greenhouse gas into kind of a growing and strengthening material, but instead of CO2, which is kind of relatively abundant compared to methane everywhere, methane emission is actually really concentrated in kind of the one place that we're looking at now is the infrastructure to transport this fossil fuel, right? So roughly 3% of all methane that we use just is leaking from the pipes. I live in Boston, and so the infrastructure here is very old actually, and so you have this very very leaky infrastructure, and actually on these small cracks or these small leaks, we actually can work with kind of, we see very high concentrations of methane, right? It's roughly like pure natural gas, 90 mole percent methane, and so we're kind of targeting, say, the same materials that grow and strengthen, but actually can grow and strengthen and kind of close up and clog these leaks that are happening with this infrastructure. Yeah.
So you have a self-healing pipe, so to speak.
Yeah.
That sounds very promising. Well, cool. Well, I definitely look forward to continuing to follow your work and your lab's work with Michael Strano. And thanks again for coming on. This has been fantastic. I learned something today, which is always a good thing. Yeah, so thank you for coming on, Daniel. Anything else you want to say to the viewers, or?
No, that sounds great. Thanks for having me. It was a wonderful conversation. Yeah.
Well, thank you. You have a wonderful rest of your day, Daniel.
Thank you. You too.